Hello once again. Today we shall be discussing on how to calculate the stresses in the fiber and the matrix of a composite. Now let's read through the question given today. A unidirectional composite bar is made with carbon fiber and an epoxy resin. It has a cross-sectional area of 1 times 10 to the power negative 4 meters square and has been cured in an autoclave at a temperature of 180 Celsius. The volume fraction of the fiber is VF equals 0.55. The carbon fiber has property EF, which equals 320 times 10 to the power 9 Newton per meter square, while the temperature constant equals negative 0.1 times 10 to the power minus 6 degrees Celsius. The epoxy matrix has property EM equals 3.5 times 10 to the power 9 Newton per meter square, while the temperature constant of the matrix equals 50 times 10 to the power negative 6 per Celsius. The bar is subjected to 1 kilonewton load at an ambient temperature of 5 degrees Celsius. Now calculate the stresses in the fiber and the matrix. Now, today we have a unidirectional composite given here in the schematic. We have the force tending towards the right, which is 1 kilonewton, and the other force is tending towards the left. So the force tending to the left will be the force for the fiber, FF, and the force for the matrix, FM, which give us VFA sigma F. And on the matrix, the subtraction of the volume of the fiber multiplied by the area multiplied by the QM given. Also, by using the equilibrium agreement, which assume that the force acting towards the right, which is the stress acting towards the right, which is F over A equals VF Q sigma F plus 1 minus VF into bracket QM equals 1. That gives us equation 1. Now we assume also that the composite has a compatibility agreement, which gives us the strain of the fiber equals the strain on the matrix, which equals the full strain given. Also, we agree that the composite is under constitutive equation. So that gives us sigma F, which is the stress on the fiber, equals EF, that is the modulus of fiber, multiplied by the strain minus the constant of the temperature of the fiber multiplied by the temperature gradient, also for the matrix. Now let's pull out the parameters. We have our A, which is the area of the whole composite, 1000 times 10 to the power minus 4. We have the temperature gradient on the autoclave, that's negative 175. We have the volume fraction of the fiber, 0.55. We have the volume fraction of the matrix, 0.45. And we have the modulus of the fiber, 320 giganewton per meter square. We have the modulus of the matrix, 3.5 times 10 to the power 9. We have the temperature constant on the fiber, which is negative 1 times 10 to the power minus 6. We have the temperature constant on the matrix, which is 50 times 10 to the power minus 6 per Celsius. We have the force acting or the load acting subjected to the composite bar, which is 1 kilonewton. That gives us 1000 newton. Don't let us forget that the temperature of the ambient, which is 5 degrees Celsius, and the autoclave temperature, which is 180 Celsius, we subtract it from the ambient from the autoclave. That gives us negative 175. Now, in order for us to find the strain using the constitutive agreement with the equilibrium agreement, so we substitute equation 3 in equation 1. So by substituting equation 3 in equation 1, we have the following agreed equation. So our VF, EF into bracket strain minus Q sigma F multiplied by temperature gradient plus the volume fraction of the matrix multiplied by EM multiplied by E minus sigma of the matrix multiplied by the temperature gradient equals F over A. By substituting all our parameters, we have our strain calculated to be 152 times 10 to the power minus 6. 152 times 10 to the power minus 6. So that gives us 152 micro. Now, by substituting our calculated strain, which is 152 times 10 to the power minus 6, into the formula given above, we calculate the stress on the fiber that gives us negative 7.36 megapascal calculated. Also, the same way we substitute the calculated strain into this formula, QM, that gives us the stress on the matrix, which gives us 31.20 megapascal calculated. Thank you very much.